In this module, we'll talk about ultramafic rocks that derive from the mantle and where we find ultramafic rocks in ophiolites, xenoliths, and kimberlite pipes. And then a little bit about serpentinization and other kinds of alteration that you're seeing in rocks. Ultramafic rocks come from the mantle. They're only found in the mantle, or when we see pieces that of mantle rocks, or those ultramafic rocks that are brought to the surface one way or another. So where we've been talking about the oceanic crust being basaltic, so a good example of mafic rock, and the continental crust being much more felsic, generally andesitic or granodiorite composition if you were to consider all the rocks that are in the continental crust. And all the ultramafic rocks are those rocks that are in the mantle. And that includes everything that includes the upper part of the mantle lithosphere that is rigid and solid, and everything down to the core. So all of these rocks, the ultramafic rocks, are much more rich in iron, magnesium, calcium, so rich, contain less silica, and are enriched in the compatible elements. I'll just abbreviate that there. So like nickel and chromium I happened to mention the other day. So their chemistry are, the chemistry of the ultramafic rocks is quite different, and you'll see that we mostly see minerals that are in the upper part of Bowen's reaction series in them. All right, where do we get mantle rocks on the surface where we can look at them? We see them in ophiolites, and those are the pieces of oceanic crust and the uppermost part of the mantle that get abducted or thrust onto the edge of continents or island arcs, or that are exhumed within the subduction zone. We can also get samples of ultramafic rocks from dredging along oceanic fracture zones, the high points in the ocean floor. We also see nodules or xenoliths in some basalts. I've mentioned xenoliths before, but that word itself, the xeno part, refers to foreign, like xenophobia, and lith, of course, is rock. So the basalts that erupt on Hawaii, for example, oftentimes bring up xenoliths of dunite, which is an ultramafic rock that is largely comprised of olivine in them, and I'm sure you've seen them before. If not, you'll see them in class. Or ultramafic rocks are brought up in Kimberlite volcanoes, and Kimberlites are an ancient kind of volcano. We have no modern Kimberlites that erupt into the cratonal areas of continents, so the older parts of continents like South Africa, parts of Australia, or the Canadian Shield. And these Kimberlite volcanoes are where we get large diamonds that are used in jewelry. And those are coming from deep in the mantle and bringing with them ultramafic xenoliths. Here's a dunite xenoliths in basalt, and this is what I was mentioning. So these are not phenocrysts. They're not early forming crystals in a basaltic magma. These are actually pieces of mantle that have been ripped off the mantle lithosphere and brought up in the basalts as in Hawaii. Kimberlite volcanoes. This is a picture of Kimberley mine. This is one of the oldest, largest mines in South Africa, where they mine for diamonds. And it's very steep-sided here. It's filled with water. I'll show you a diagram in a moment why it's so steep-sided. But these pipes shoot through the mantle and through the Earth's crust very rapidly and explosively erupt onto the surface, and in that process are ripping up pieces of mantle that it bring along with it. And I mentioned that you see diamonds coming up in kimberlite volcanoes. And then just notice these minerals here, the very green diopside and the very purple or pinkish purple garnets that come up in those kimberlites. And this results from a lot of chromium, which is a compatible element. And these are magnesium-rich pyrope garnets. And because kimberlite volcanoes don't form a nice pointy peaked volcano, steep-sided, that stands out of the landscape and forms large mountain belts, they are really flat. Their surface expression is very flat. You could walk across it and never know that you are on top of a kimberlite volcano. And it's these pyrope garnets and these chrome diopsides that allowed discovery of kimberlite pipes in Canada relatively recently. Okay. Here's a cross-section through what a kimberlite pipe looks like. And I mentioned just now that the surface expression is very flat. It's not a pointy peaked volcano. But you see these steep sides in this portion that reaches the surface. That's why the Kimberley mine was so steep-sided, because they literally mined straight down just in the kimberlite pipe. And in part, that's how they know more of the structure of the kimberlite. But these volcanoes they're thought to be brought up in a matter of days, maybe even hours, from deep parts of the mantle straight to the surface. So these would have been really impressive and impressively dangerous things to be around when they erupted. But as I said, they are no longer around. We're not having modern kimberlite volcanic eruptions anymore. Here's a map just to give you an idea of where kimberlite volcanoes are located. And I'm just going to use a map of diamond mines around the world to do that. So these mines, the most productive ones are probably in Siberia, in Russia, in South Africa, in Australia, and India. And then I mentioned those in northwestern Canada. There are also some in Brazil. And these are all locations of kimberlite volcanoes in the ancient parts of the continent, so in the cratonal areas or near the cratons. Here's an idealized cross-section of an ophiolite, and I mentioned ophiolites to you already. And no wonder you look puzzled, because I thought I had already spoken to you about the ophiolites, but it turns out that was in this lecture. So here we go. We'll review a little bit then. Most ophiolites, most locations where there are ophiolitic rocks on continents are only partial ophiolites. And in the Franciscan, we only see the topmost part of the ophiolite. We see the cherts that are those result of deep sea sediments, pillow basalts, and the basalt that's underneath the pillows, just directly beneath the surface of the oceanic crust. So the seafloor, where the basaltic eruptions are actually coming out on the seafloor, that's where you get these pillow basalts, where the pressure of the overlying water forms them into somewhat spherical blobs. and they crystallize like that. Beneath that, basalt's crystallizing, but it's not going to have the pillow form. We see that all over in the North Bay and elsewhere. And we also have some of the ultramafic rocks that were brought up, probably not scraped off with the ophiolite, but preserved in the subduction zone, and actually came up in the subduction zone. And I mentioned Ring Mountain has some pyroxenites. I'm saying pyroxenite. It's a generic term for an ultramafic rock that is comprised mostly of pyroxene. And we know the complete section of ophiolite because there are a few places like Oman that have a complete section preserved. And those contain sheeted dykes, gabbro, which is the plutonic equivalent to the basalts that were erupted in the oceanic crust. So the gabbros are further down, and then we get into a layered gabbro where we see actual crystals forming a layering as they crystallize and settle out of the gabbro. And beneath that, we have the crust-mantle boundary. So this is crust, oceanic crust, above, and this is mantle below. And so when we get ophiolite sections preserved, we're getting the whole oceanic crust and a bit of the mantle preserved with it. Here's a picture of some radiolarian chert that forms the nice red cliffs along the roadway just north of the Golden Gate Bridge. Here's an example of pillow lavas, and this is from the Oman ophiolite. And you see the nice rounded form that they have. That's the top of the oceanic crust. That's the sea floor right there. Beneath that, we have sheeted dykes, and so you should be seeing the sheeted nature of these dike intrusions, the basalts. We have gabbros beneath that, so it's the plutonic equivalent to the basalts that were erupted. Beneath that, this cumulate layering. So this is literally where you're seeing layers of, let's say, olivine or pyroxene deposited by crystals settling out of a melt as the gabbro cooled and crystallized. So this is the bottom part of the oceanic crust. And beneath that, we have the mantle rocks, and this is a serpentinized pyroxenite. So this is the pyroxenite here in that's weathering a rusty red, and then that's probably instatite. And we also have these veins of serpentine minerals that form when you alter the mantle rocks. And so the serpentine minerals replace the magnesium minerals in the pyroxenite. And that's very commonly when you see mantle rocks, you see that they've been serpentinized. And there's many opportunities for hydrothermal fluids, so meaning hot fluids, either from the ocean that are circulating through fractures in that oceanic crust in the uppermost mantle, or this is happening in the subduction zone before the rocks are returning to the surface. We have lots of serpentinite. So this is those ultramafic rocks, but that have been completely replaced by serpentine minerals to form a rock that we call serpentinite. And this happens to be Baker Beach, just south of the Golden Gate and just west of campus. And this is typical. You see it all along 280. This is probably the most abundant rock that we have in the Franciscan complex around here. So lots of opportunities to see serpentinite. Now, the serpentine is an alteration mineral where we're replacing parts of the pyroxenes in those peroxenites with the serpentine minerals. You've been seeing much more common kind of alteration in chlorite that's replacing biotite. So there's a nice, pretty well preserved biotite there. But you see the edges around, just around the edges, it's starting to turn green. That's the chlorite replacing the biotite. Again, the magnesium and iron-bearing minerals are what get replaced by chlorite. And it may be complete replacement, like down here, or it may be a partial replacement like this, or maybe it's just along fractures, but that's very common to see, and it's not just in ultramafic rocks. I'm showing you an example that you would see in metamorphic rocks or igneous rocks. And here's another example with chlorite replacing garnet in a different kind of rock. So also, again, iron and magnesium bearing minerals get replaced by chlorite often. So what did you learn in this lesson? That mantle rocks or ultramafic rocks are found in ophiolites, mantle xenoliths, and kimberlite. That ultramafic rocks are often serpentinized. And a common kind of alteration that you see in rocks is where chlorite replaces iron and magnesium bearing minerals like biotite and garnet.